Okay, we're about to start learning about an area of chemistry that's going to have some applications that spread over all kinds of areas. Other science areas, other math areas, a lot of things are going to help you in life. Stoichiometry, that's what we're talking about, stoichiometry. We're going to start off learning about something called mass-to-mass stoichiometry, and we'll branch out from there. Okay? Mass-to-mass stoichiometry. Now, let me give you mass-to-mass. Let me give you a definition of stoichiometry first, and then we'll talk about what mass-to-mass stoichiometry. Actually, mass-to-mass should be evident from the definition of stoichiometry. Stoichiometry I like to define as the math in chemistry that requires a balanced equation. The math in chemistry that requires a balanced chemical equation. So mass-to-mass stoichiometry then would be the math in chemistry that requires a balanced chemical equation to get from the mass of one compound to the mass of another. Does that make sense? So if the definition of stoichiometry is the math in chemistry that requires a balanced chemical equation, then the mass-to-mass stoichiometry would be the math in chemistry that requires a balanced chemical equation to get from the mass of one chemical to the mass of another, mass to mass, right? And that's what we're going to be spending our time today learning about. And we'll put it into bigger and bigger things as we go along in this unit, okay? Now, a couple things you need to know about to do mass-to-mass stoichiometry, and one of them is to know how to calculate what's called molar mass. Molar mass is found by adding up all the atomic masses of all the atoms in a chemical formula. The atomic masses come in atomic mass units. Now, we used to write the shorthand for atomic mass unit as AMU, but chemists got lazy and shortened that to just simply the lowercase letter u. Okay, so an atomic mass is unit of just the letter u. Okay, but when you're finding the molar mass, you don't write the mass you sum up at the end in u's, you write it in units of grams. Okay? So the sum of all the masses of all the atoms in a chemical formula written with units of grams. Now what's a molar ratio? Okay, a molar ratio. A comparison of coefficients. A comparison of coefficients in a chemical equation written in a fraction. Let's see, let's start with something kind of simple in terms of chemical equations. Miguel, if I run this chemical reaction in water, what physical state symbol do I assign to this chemical right here? Where on the periodic table is zinc found? Okay, it's right here. All right? The stair step that divides metals and nonmetals goes right here. Oop, I skipped one, okay? Everything on this side over here, all this stuff over here, those are metals. And we did cover that in Unit 1. No, Unit 2, right? What were the metals and nonmetals, right? Well, all these, unless you really heat them up, they're going to be solids. Okay? You got to get them pretty hot to get them to be a liquid, but mercury, of course, is a liquid at room temperature and pressure. So, this is a solid. Colin, what physical state symbol, if this is in an aqueous environment, what physical state symbol do I assign to this chemical? Why? That's your claim. Yes, it's going to be aqueous. I'm not saying yes. I'm just saying you're saying your claim is aqueous. Now, give me your evidence and your reasoning.
It would dissolve in water.
Okay, that's your reasoning. What's your evidence? What evidence do you have that this dissolves in water? You think you got it? You want to steal?
Sure.
Okay. Steal. Go ahead.
All chlorides are soluble.
All chlorides are soluble. There's some exceptions. Hydrogen's not one of them. Okay? That's one reason. Okay? All right? That's the evidence. But there are other evidences, okay? You know that most strong acids are going to dissolve, strong acids, period, are going to dissolve in water. That's another evidence. You can use that as your evidence, okay? All right, so this is aqueous. All right? Julia, What's going to happen in this reaction if it occurs at all? Or will there be a reaction at all? Maybe that's the first question I should ask. Will there be a reaction at all? How do you know that? That's your claim, yes. Now, what is your evidence, and then what's your reasoning?
Because zinc is more active.
Zinc is more active, okay.
It's going to go with the polymer.
It's going to go with the what?
It's going to go with the CL.
Okay, going with CL. I just misunderstood what you said. I thought you said polymer. Did you say polymer? Okay, that's all right. That's all right. It's kind of hard to keep all those terms straight, isn't it? Okay, so the zinc is going to go with the Cl. The hydrogen is going to be by itself. All right, good claim, evidence, and reasoning there, okay? All right, so here's our hydrogen by itself. What physical state do I assign to this, Tanner? Well, phone a friend. It's a gas, you said, okay? Why would you say it's a gas?
I don't know.
Well, I've told you hydrogen is going to be a gas. Whenever we do a single replacement reaction and we displace hydrogen from an acid, we always get hydrogen in the form of a gas. Every time. Okay, there's your evidence and reasoning. Mr. Tedder sets up. Dalton, what form do I write? What else do I need to write for the form of this hydrogen? H2, I hear somebody said. Well, and the only evidence and reasoning you have for that is because I told you it had to be that way. Okay? But you could also look at your standard reduction potentials, and you'll see that hydrogen ions become H2. Okay? This is a molecule of hydrogen gas. Hydrogen gas is in the form of H2, as are oxygen, nitrogen, chlorine, fluorine. Okay, all of those are diatomic gases. So in their natural state, they're going to be, when they're by themselves, they're going to be in those gaseous diatomic forms. Okay, all right. And I think that we had somebody already say that we're going to make zinc. We're going to put zinc with the chlorine. Ashley, what else do I need to do to finish this? Just give me the state. Chlorides are soluble with some exceptions. Zinc is not one of them. Okay, there's your evidence and reasoning. Okay, chlorine, bromine, iodine compounds are soluble with some exceptions. This is not one of the exceptions. Are we finished with this? Okay, what charge does zinc have when it's in a binary compound? And tell me how you know. How do you know?
Because it's on the periodic table.
Okay, well, so this position on the periodic table here, everything in this column is a 2+ charge, except that mercury can also have a 1+ charge. Okay, all these in this column are 1+, 2+, 3+, 2+, except for mercury, and 3+. Okay, and whenever you have monoatomic anions by themselves, all of these are 1 negative, 2 negative, 3 negative. Okay, all right. That's just repeating the last unit. So what charge does the chlorine have? So we're going to let Audrey try this. All right, Audrey, tell me what to do to balance this formula. Haley says we need...
You put a 2 after the ZN.
There you go. After the ZN? Oh, no, you didn't say that. Oh, no. I just misheard you. Okay, all right. Wow, you got to do all this stuff before we can even do stoichiometry.
I remember now because chlorine's 1 minus 2 for the
There you go. You got it. You got it. All right. I know you figured it out. I know you figured it out. And Haley, you deserve a gold star for being brave to speak up and trying to try this out. Okay. All right. Good.
Katie deserves a star too.
What?
Katie deserves a star.
She deserves a platinum star.
Gold.
You want gold? You like gold better than platinum? Okay. You say so. Okay. I thought you'd ask for diamonds or something. Okay. All right. So here, can you balance the equation? Can you balance the equation? Balance the equation. Stoichiometry requires that you have balanced equations, okay? But in here, you can't just say it's done. You got to show me because I'm from Missouri. So and you show me using what? Atom inventories. Please do that. So we're going to make a list here of all the elements we have in our equation. Make a kind of simple little spreadsheet, count up everything. Put a coefficient of 2 in front of the species carrying the hydrogen on this side, and turns out it's going to balance the whole equation just by that one coefficient there. And so now we have a balanced equation. Okay? Alright. Molar ratios. We said molar ratios are just a comparison of the coefficients in front of the chemical species in a balanced chemical equation. And we now have a balanced chemical equation. Okay? I have a dozen different molar ratios that I can write, because I also said they have to be in the form of a fraction, or they're usually in the form of a fraction. Okay? So if I have 1 mole of zinc, how many moles of hydrochloric acid do I have? 2. So I could write this ratio. Or I could write this ratio. And if I have 1 mole of zinc, how many moles does that compare to in the number of, or the moles of hydrogen gas? I can compare zinc to zinc chloride. I can compare 2 moles of hydrochloric acid to the 1 mole of hydrogen. Dozen different molar ratios from one equation with 4 species. That is a lot. But in any particular mass-to-mass stoichiometry problem, or any other kind of stoichiometry problem, just one simple problem, you only need 1 of these. You have to figure out which one you're going to need. Check it out. Write it down. I want to show you how to solve it. Using 1 of these, of the choice of 12 molar ratios, we're going to choose the one that's going to solve this problem. So if we have 12 moles of, what was it, zinc? Okay. What's our starting amount? Okay. And if you reviewed, as I asked you to, the process we use for solving conversion problems in this class from Unit 1, what do I do with that starting amount? How do I start with that? All right, starting amounts always go over 1, okay? And then we just need to pick out which one of these molar ratios is going to get us where we want to go.
First one.
The very first one. Okay, why does the first one give us what we want to get? Give us what we need to get where we want to go. The HCl's cancel each other out. Wow. Jenny is on fire. Cancel out moles, cancel out HCl, and we have nothing but moles of zinc left, and that's what our question asks. Okay, which happens to be 6.00 moles of zinc. Okay, why 6.00? That's 3 significant digits. This has 3 significant digits. These 2 numbers are counting numbers. They're infinitely significant. We don't consider them when we're trying to figure out how many significant digits we have in a final answer. Okay? Multiplication and division, you always find the measured or calculated number in the problem that has the least number of total digits and round your final answer to that same number. Or in this case, we had to put 2 zeros on there after the decimal to give 3 significant digits. That makes sense? That seems pretty simple, right? Let's try this one. To solve this problem, anytime you have to go from one chemical species to a different chemical species, you have to have a balanced equation. You got me? Anytime you go from one chemical species to another, you've got to have a balanced equation. Okay? Because you've got to go through Moleville. I'll explain that later. All right. So here we have nickel reacting, if it does at all, with copper nitrate. Copper has a 2+ charge. Nitrate's one of those polyatomic ions you have to memorize. And we know it's copper 2 because the word copper 2 tells us it has a 2+ charge. There's also a copper 1, but this one's copper 2. Nitrate is one of those polyatomic ions you have to memorize. It has a 1 negative charge. To charge balance this formula, got to have 2 nitrates. Okay? Now, in an aqueous environment, nickel is a metal. It's going to be a solid. Okay? Nitrate compounds are always soluble. So this is aqueous. And if a reaction occurs at all, nickel has to displace the copper. Nickel is more active than copper. If you're using the activity series, nickel's higher than copper. If you're using the standard reduction potentials, nickel is lower than copper 2. And so nickel displaces copper. We're going to put the nickel with the nitrate. Nickel is always 2 plus. Nickel is always 2 plus. So we're going to need 2 nitrates to balance this formula. And that means we're going to end up with copper, the metal, all by itself. Now then, we need to balance the equation. To do that, we're going to use an atom inventory. It's required in this class. Alright, so yes, I know it's already balanced, but this is how you show me. Okay? Now, the question is, if I start out with 5 moles of nickel, and it's reacted with copper nitrate, how much of the copper nitrate will be used up? Well, that means 5 moles of nickel is the starting amount. We're going to put that over 1. Always put your starting amount over 1. There are times when you don't, but almost everything that I can think of we're going to do in this class, starting amounts are going to go over 1. It's just kind of a shortcut to remind you what to do. All we need is a molar ratio now to get me from nickel to copper nitrate. And since a molar ratio is a comparison of the coefficients in the balanced equation, we have 1 and 1. So we're going to put 1 mole of nickel on the bottom because that's going to allow me to cancel nickel. And 1 mole of copper nitrate on the top because that's where I want to get to. Oh, I should put moles. Moles, copper nitrate. Cancel as I go. And we get 5.0 moles of copper nitrate. Seems pretty simple, right? So, now it's time to try this one. So if we're reacting sodium carbonate with a hydrobromic acid, sodium carbonate is Na2CO3 because sodium has a 1 plus charge, carbonate has a 2 negative charge. That's what it takes to balance that. And we're reacting that with hydrobromic acid, that's HBr. That's going to be aqueous. Sodium compounds are always aqueous. Acids are almost, strong acids anyway, are almost always aqueous. Then we're going to put these together. We get sodium and bromine. Sodium goes with the bromine over here. That's aqueous. And then the hydrogen is going to go with the carbonate. That looks like it's aqueous, and in fact it is. But anytime you see H going with carbonate, and we haven't balanced the formula yet, it comes out to be this. This should send off bells and whistles in your head, because this always breaks down into H2O and CO2, and there's your driving force for the reaction. So this is gone, that replaces it. Okay? Then we're going to balance the equation using an atom inventory. Just for time, I'm going to skip the atom inventory because we've covered that several times. We know that this is going to be balanced when we do this. Okay? If our starting amount is 7.25 moles of sodium carbonate, then we're getting a molar ratio to get from this to this. So we have one of these. The coefficient here is 1. The coefficient here is 1. So we're going to put 1 mole of sodium carbonate on the bottom here, because that allows us to cancel moles and sodium carbonate. And on the top then we're going to put the 1 mole of CO2, and that's going to give us 7.25 moles of carbon dioxide. Okay? Pretty simple once you kind of get all the pieces together. Alright? Now, I want to cover calculation of molar mass really quickly, okay? We're going to calculate first the molar mass of sodium carbonate. And there's a way I want you to do this every time. It's a process that's going to save you some trouble later on, and it's going to make it easier for me to find when you make mistakes. And the way I want you to do this, remember the molar mass of any substance is the sum of all the atomic masses of all the atoms in the formula written in units of grams. Okay? So what I want to do here is, since I have 2 sodiums, I want to put down the molar mass, the atomic mass, 22.99 on your periodic table. And I'm just going to multiply it by 2 because this is adding sodium's atomic mass twice. Okay? And then carbon, I've only got one of those, 12.01. times 1. I'll go ahead and do that 1 here. And then oxygen, I've got 3 of those. 16.00 times 3. And we're just going to do the math here real quick. 45.98 and 48 down here. And we get 105.99 grams. Okay? Now that's the molar mass of sodium carbonate. And if that were the only question, that would be the answer. What's the molar mass? But in order to make all this stoichiometry stuff work out for you better, I'm expecting you every time to do more than just this when you calculate the molar mass. I want you to write it's grams of sodium carbonate, and I want you to write that that's equal to a mole every time. Okay? So let's calculate the molar mass of carbon dioxide now. You'll see what I'm doing? Adding up the atomic masses, just finishing out in this. So I've got what I call an equality statement here, where I say the molar mass of this species is equal to a mole of that species. Okay? So if we calculate the molar mass of carbon dioxide, we just got carbon and oxygen. We already know carbon's 12.01. We have one of those. 12.01 AMU, which we write just simply with the lowercase letter U. That's our symbol for atomic mass unit. And oxygen is 16.00. We have 2 of those. That's 32 AMU. We add them together, we get 44.01 grams of CO2. And we're going to say every time we write this that this many grams of this stuff equals 1 mole of this stuff. Now, using what we talked about earlier in the class, we can write 2 different ratios from this, can't we? Okay? Actually, we talked about this in Unit 1 as well. If this equals this, I can put it in a fraction that equals 1 by putting this on top of this on top. So 105.99 grams of Na2CO3 over 1 mole Na2CO3. And because these 2 values are equal, the fraction overall is equal to 1. And we have what's called a conversion unit. But I can also write 1 mole of Na2CO3 over 105.99 grams Na2CO3. And that also equals or has a value of 1 because those 2 things are equal. I can do the same thing down here. Can you write those molar ratios? It's called a molar mass ratio now. Okay? Can you write that? So every time you've got a molar ratio equality statement, which I want you to write every time you do this, you can write 2 different molar mass ratios. Okay? We need to figure out which one we want to use for a problem. We just don't have the right problem yet. So let me show you the right problem. It's the same problem, but I kind of changed around some of the wording more or less. Okay? In this case, we're starting with 7.25 grams of sodium carbonate and reacting it with an excess of hydrobromic acid. We're going to calculate not the moles, but the mass of carbon dioxide. To solve this problem then, I want to take a sheet of white paper and turn it sideways. So it's going to make my life a lot easier by doing it that way. Okay? What's our starting amount? 7.25 grams this time of sodium carbonate. And put it over 1 because the starting amount, that's what we do with starting amounts. Okay? But this time, in order to get from the mass of this to the mass of the CO2, I've got to first convert to moles. Because we've got to go through moleville. Okay? You can't go straight from mass of this to mass of something else. You've got to go through moles. And to get to moles, we're going to use one of these 2 molar ratios. And which one of these 2 do I want to use here? Well, if I have grams on the top here, I want grams at the bottom up in the next step. So take that one. Okay? So let's see, 1 mole Na2CO3 and 105.99 grams of Na2CO3 on the bottom here. Well, let's cancel. Cancel as you go. Guess what? We are moles. We're in the outskirts of Moleville, guys. Well, I got to get from moles of this to moles of the other thing, because you got to go through moles to get to the second species. Anytime you go from one chemical species to another, you got to have a balanced chemical equation, because you need a molar ratio. What's the molar ratio between sodium carbonate and carbon dioxide? We used it in the last problem. You know, there's our molar ratio from the balanced equation, right? 1 and 1, 1 and 1. 1 mole Na2CO3, 1 mole CO2. Keep it simple. Cancel as you go. We are now at moles of CO2. How hard is it to get the mass now? What do you need to get from there to mass? Which one of these two ratios am I going to use to get to the mass of CO2? Top one. Because it's going to allow us to cancel out the moles. 1 mole of CO2 goes on the bottom. 44.01 grams of CO2 goes on the top. I can simplify. And all that, just do the math and it'll get you the grams of CO2, which is what the question asks for. The central thing is this molar ratio, okay, from the balanced equation. And you go from mass of this to mass of this, you've got to first convert 2 moles using the molar mass ratio. Once you have moles of this, you convert to moles of the other thing using a molar ratio. And then once you have moles of the second thing, use another molar mass ratio to get to the mass. Plug it in the calculator and see what you get. Well, let's write down the whole answer. Now your calculator may have one or more digits less or more than mine. Okay? This is grams of CO2. Now let's evaluate our problem and figure out how many significant digits we need in the final answer. From Unit 1, how many significant digits do you need in a final answer when you're doing multiplication and division? What? Yeah, 301, but 1. Okay, so there's 3 digits in this measured or calculated number. And you're looking at the measured or calculated numbers here. This is measured, calculated, and these numbers here, and even here are really just counting numbers, and they're infinitely significant. We don't even worry about those. Okay? The simple thing is look for the measured or calculated numbers, find the one with the least digits, round your final answer to that same number of digits. So you want to write out the full answer, underline the insignificant digits, so that's everything after the first 3 digits here. Draw an arrow to show that you're rounding off because nothing else will do. If you're going to round off, you've got to show an arrow, not an equal sign, not a squiggly equal sign. Those mean different things. So we got 3.01 grams of CO2. And that's the way you solve a mass to mass stoichiometry problem. Okay? First you got to have a balanced equation. So there's our balanced equation we already did earlier. Okay? You start with your starting amount over 1. If your starting amount is in mass and you're trying to get to some other species, whether it's the mass of the other species or the volume of the other species, whatever way you're trying to get to the second species, you've got to convert the starting stuff to moles. And that's what molar ratios are for. And once you've got moles of one thing, you get to moles of another thing using a molar ratio. And that comes from a balanced equation. Okay? Got it? So your homework is on the board, which is a stoichiometry, a mass-to-mass stoichiometry problem.